选择，仔细看着把家讲的装独特。我说亲爱亲爱的，我们故事说到这。
那张侦探攀上生锈的小方船，像蝴蝶离不开有花香的地方。宁静的小巷，一杯永和豆浆，我在细细品尝恬淡的家乡。霓虹灯点亮关于夜市的想象，孩子们捉迷藏，在找爱吃的糖。昏黄的夕阳，龙山寺的老墙，我虔诚点着香，守那一株希望。可以许下愿望就别等。
许个愿吧。
那张侦探攀上生锈的小方船，像蝴蝶离不开有花香的地方。宁静的小巷，一杯永和豆浆，我在细细品尝恬淡的家乡。霓虹灯点亮关于夜市的想象，孩子们捉迷藏，在找爱吃的糖。昏黄的夕阳，龙山寺的老墙，我虔诚点着香，守那一株希望。少一点伤痕，多一点的掌声，少一点战争，多一点的单纯。
着耕作，名牌大小包，女人爱不释手，西餐厅最佳主角也是我。祝福大家 Happy New Year。
Well, so I bet many of you probably already know that, well, 2 days later is Chinese New Year's Eve. And according to the Chinese horoscope, I believe you guys must know that the upcoming year is the year of ox, or say the year of cow, whatever, how you call it. So that's why we play that song. Well, in some sense, we also tell you how important cows or ox or whatever, how you call them, how important they are in your life, but also give you some feeling about the atmosphere of Chinese New Year. And hopefully some of you are still in the States but cannot enjoy the Chinese New Year with your friends or family. You will feel a little bit warm after listening to those. And some of the music video, I think they are pretty funny. So definitely take a look of it. But before the Chinese New Year's Eve, I believe there are still some important things that I have to teach you, which is around about virtual memory policies. So before we start talking about those policies, it's still important to tell you why we are here. So after we're talking about virtualizing a processor as part of the important mission of the operating system, we start to talk about virtual memory. So regarding the idea of virtual memory is that we create an illusion of memory space to every running application, every running program, which is process. And every running process, they would assume that I have a complete virtual address space from 0 to the topmost address is free for me to use. However, this address space is usually larger than your physical memory. So apparently the operating system is doing something to help us manipulate the mapping dynamically for each region of your virtual memory space to the physical memory location, and try to interleave the usage of physical memory for multiple different processes. So the most commonly used mechanism is called demand paging and swapping. So the idea of demand paging and swapping is that, first of all, by paging, it means that we partition the memory address space both in the physical memory locations and the virtual memory space into fixed size chunks called pages. And whenever you are requesting an address, we not only check if the requesting byte is in a memory, but also if the whole page is in a memory or not. When a page is not found, which means that you cannot find a mapping between the virtual page to the physical page, it means that the page is not allocated to physical memory location. Then it will trigger a page fault exception, require your operating system kernel to handle that exception. In a way, how the operating system kernel would handle it is that we check if there are space available, if there is any space available on the DRAM. However, most of the time you are going to running out of space. Then what will happen is that we will figure out if there is a page that we should kick out. And if that's the case, then we should kick out the page and store it on a secondary storage so that you can make space in the DRAM for the upcoming page to fit in a DRAM. So that's the basic idea of demand paging and swapping. And whenever you need the page that you moved to the secondary storage, then you go through the same process but swap the page back. So that's why it's called swapping. And so in this kind of demand paging plus swapping mechanism, there are still quite a few performance issues we have to deal with. So one of the things that would be pretty annoying is that if you think about how big the memory space we have, we actually need a large page table to accommodate all the mappings, which is not possible to be residual in a memory. So if you want to make your demand paging page table to be fit in a memory, there are two things you have to do. First of all, you have to make it pageable. So by pageable, it means that, well, we only need a portion of the page table to be reside to be residual in your memory. And whenever you need other nodes, you can potentially swap in and out, like what we just mentioned for demand paging. So in this way, you can save the working set size of your page table in the memory. And the second thing is that the whole table itself, we can actually save the space by not allocating those page table entries are not mapped. So in this way, we decide the hierarchical page table take advantage of this. First of all, we break up page tables into small page table nodes, and each page table nodes is exactly the size of a page, so that we can swap in and swap out in a page granularity easily. And the other thing is that we don't allocate those page name nodes belongs to address that are not used. So whenever you have a context switch, all you need to do at least is that you program your page table base register and load the root node, which is this one, of your hierarchical page table to your main memory. And then, well, if we found, well, this node is a page fault, then you can gradually bring in those page table nodes. And if those page table nodes are already in the memory, you can keep traversing until you find the final translation. So that's the whole idea of hierarchical page table node. So in this way, you can imagine that hierarchical page tables help us to save the space. However, a cost you have to pay is because each time when we have to translate, we have to go through multiple page table nodes. So the traversal time of the page table is getting longer. So that's one thing, right? We solved the translation overhead, but how about the page replacement policy? So as we calculated before, even though the percentage of page fault is only 0.1%, we still have an effective memory access time as long as 10,000 nanoseconds, which is 100 times more than your DRAM access time, or say 20,000 times of your processor speed. So that's definitely not acceptable, right? So we need a better page replacement policy to make sure that the probability is as low as possible. So that's what we are going to discuss today. And previously, we also mentioned that the VAX VMS system, they already try to address that through mechanisms like page clustering and page caching, in a way that they try to keep those modified page and as well as those pages that are kicked out from the working set of a program still in somewhere in the DRAM. So whenever you need it, you can still find it, and to reduce the chance of swapping in and swap out. So that's the basic idea. That's one of the optimization we have seen in the last lecture. And then another thing that we have to take care is that, okay, we want our operating system to be portable and fulfill the demand of multi-processor hardware. So Mach virtual memory design, which is the paper called Machine Independent Virtual Memory Management for Page Unit Processor and Multi-Processor Architectures, is actually promoting this idea. Although a lot of the data structure here seems not super efficient, but if you look at this slide, none of the data structure regarding to the Mach's VM management system is machine dependent. The only thing that is machine dependent is how a structure called PMAP regarding how are they going to cache the page table. However, except for that, everything else is machine independent, allowing Mach's kernel to be easily ported to multiple different platforms. And that's one of the reasons why Apple or Microsoft, they adopt Mach's idea in terms of virtual memory management. And the other thing is that if you look at the address allocation in multi-threaded model, you will figure out that there are a lot of unused area in the address space. So the linked list idea that Mach promotes is actually not too bad in terms of the sparse matrix multiplication, sparse multi-threading model, because it would help us to more efficiently use the memory, the mapping table, and improve the space efficiency. However, if you have a hierarchical page table, it's probably not going to be better than this one. So that's another reason why it's embraced. So that's what we have learned in the last week. And today we are going to talk about the page replacement policies and the page replacement policy that once has been used in Unix and other popular page replacement policy that is currently universal to a lot of systems. So again, I know you spend a lot of time reading the textbooks, try to pick up your memory about the undergrad operating systems, right? So I do want you to, I don't want to waste your effort on this, so I just want you to test if you really understand the important two policies that you have learned in the past, the FIFO and LRU. So spend a couple minutes on this one and tell me, what do you feel? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looks like we need some discussion. So why don't you go ahead and start? Oh, sorry. One more time. All right, wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I do believe most of you have an answer. So can some of you tell me what your team is thinking about? Okay, Emmanuel.
Hello. So we thought in our team 2C.
Mm-hmm.
For
So how
FIFO
do you
we got
get that?
9. For FIFO we got 9, and for LRU we
How
got
do you, so what about the 9? So are we going to have page fault for the first, the zeros reference?
yes.
Okay, because now there's nothing there,
There's
right?
nothing.
And
Yeah.
we have 3 slots. So right now we have 2 and 2 entity slots, right? So how about the first reference? Is it a page fault?
Yes, because we had nothing in there.
Okay, because it's not here before, right? How about the second?
We do. It's over there too. It's right over there.
Well, what are we accessing? Well, so now how about the second reference when we access the page number 2?
There
Is
is no
there
page fault because it's inside the.
there's no page fault because 2
yeah.
is right there, right? So
Yeah.
how about the third one?
There is a page fault.
Why? Because 1 has
There is
never been
no
accessed
1.
before,
Yeah.
right?
There is no 1.
Right? So how about when we access 5 now?
There's another page fault.
And are we going to kick out anyone?
We're gonna kick out 2
Why?
because that was the first one used. First in, first out.
Okay, so now we have 531 and 5 is a page fault. And now we are accessing 2 again, right? Is there a page fault?
Yes, there is.
And are
Which
we going to
one
kick out anyone?
We will kick out 3.
Okay, so we put 2 in, kick out 3, and now we have 4. Is it a page fault again?
Yes, it is. We're taking out 1.
Okay, right. So if you keep going, you will figure out there are a total of 9, right? So how about LRU? So I believe the first 3 is probably the same, right? The
Yes.
tricky first, okay,
4.
so
The
up
first
to
4.
here is the same, right? How
Yeah.
about the fourth cycle?
And the fourth cycle.
Who are we going to kick out now?
3. No. Yes, 3. 3 is the next one we're gonna kick out because we used 2 and
Right.
1.
Why?
We used 2 in cycle 2. We used
Right.
1 in cycle
Because
3.
we used 2 at a second cycle, but for 3, it's the longest we haven't touched, right? So that's the one we are kicking out. And now in the fifth cycle, when we access 2, is there a page fault?
No, there isn't.
There is not, right? And now when we access 4, is there a page fault?
Yes, there is.
And who are we going to kick out?
We're going to kick out 1.
We are going to kick out 1, right? Because we haven't seen it for a while, right? And now, are we kick out anyone for this case? Are we having a page fault for this case?
No, because we already have 5 in there.
Right. So how about this cycle? Are we going to have a page fault?
Yes, we're going to kick out 2 and replace it with 3.
Because we haven't been accessed to for the longest amount of time, right? So if you keep going, you will figure out that for LRU, we will have a total of 7 page faults, right? So which give us the answer of C. Okay, perfect. Thanks for your help. So now I believe that a lot of you already have very good understanding about this 2 policy. And however, if you compare these 2 policies, you will figure out that, well, in real system, we actually implement more FIFO than LRU, right? Like, because LRU, you will require some hardware support or even linked list to maintain who is the least recently used. And even for human eyes, you have to check who is the earliest one, right? But for FIFO, it's pretty easy. You just need a circular queue and you know who is the oldest, right? And as you can imagine, if human beings need to spend a lot of time brainstorming who is the longest one that we haven't touched, the overhead must be high, On the other hand, FIFO, you don't have to think about that, so it's low. And the performance, well, as you could imagine, and as we just proved, right, FIFO is usually not as good as LRU. So, um, uh, um, so now I'm going to tell you, and some of you were saying about like you saw the LRU more than FIFO, but that's actually not true. If you read the papers that we have been giving you, none of them is using LRU. So now, but a lot, but being honest to you, none of them is using LRU. So and this paper is going to tell you why. And now I'm going to give you the first paper, which is converting a swap-based system to do paging in an architecture lacking page reference bits. And well, the page reference bits is actually one of the hardware support that LRU require. However, that thing, if you don't have hardware support, is very, very slow. And unfortunately, none of the hardware you have right now have this kind of hardware support. So that's why so that's why this information is really, really important. So this paper is really, really important. So let's look at, but before we start, right, it's always a good idea to look at what's the state of the art before we introduce this paper, and then you will figure out why we are talking about the virtual memory design for this paper. So this question is asking about the virtual memory system that you have seen in VEX VMS, and it's described again in a Unix virtual memory paper. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after looking at your answers, although there is one monopoly, but I do feel like we still need discussion because maybe that set you saw is not the same with the set that other people are thinking about. So go. Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so it's kind of interesting. I saw two teams has different answers. So raise your hand. Okay, so I have Rogelio. So what do you think?
Well, our team red didn't quite reach a consensus. I'm gonna go with they're all true.
Okay, so how about the blue team?
We made the same decision.
So you made you think so your group has a consensus regarding all four are true.
Yes, I think those we talked about, it seems like that all of us thought all of them are correct. At first,
Okay.
we were not sure about the third one, but then we agreed on that too.
Okay, so Rogelio, which one does your team cannot reach a consensus on it?
At first, we were thinking at least 3 of those were correct, but towards the end, we were
Which one?
Okay, so towards the end, we agree. We sort of reached that all 4 correct, but we were not so sure about the 4th one.
Okay, swap out. Well,
Yeah.
so okay, so thanks for your comments, right? But if you look at the title of this paper, converting a swap-based system, right? Swap-based system. What does that mean? It actually implies that the VEX VMS system itself is a swap-based system. But let's look at each of the sentences, right? So, VEX machine provide no hardware supports for page replacement policy, right? Like even without even this minimum page reference information, the only reasonable algorithm for the page replacement policy is FIFO or random, right? So this pieces of information tells you that all right, like operating system, like when you are in your undergrad study, you thought LRU is the policy that everyone would use, but in fact that no one can implement LRU policy because the LRU policy definitely requires some hardware support that is absent in most of the hardware, right? And plus, because this is a hardware dependent feature, right? So as our operating system try to be more and more portable, this hardware dependent feature is not likely to be adopted by the operating system design. So you cannot have your hardware, the operating system kernel to depend on this kind of hardware feature that may or may not be supported. So it turns out that, well, the only thing that you can do is FIFO, right? So that's why the first two, they are correct because, and they are related. VMS, I mean, everyone knows LRU is better, but the thing is that it's not feasible because you don't have the hardware support. So it turns out they can only implement FIFO. Now, the 3 and 4, that's something that some of you might not might not get it when you first read the paper. But as I pointed out, right, the title of this paper, it says swap based. It implies that what will happen is that, well, so first of all, each process is assigned to a fixed size memory partition called residence set. And whenever you have a context switch, whenever a process is removed from memory, its entire residence set is returned to the swap file, right? Its entire residence set is returned to the swap file. So according to this information, it tells you clearly that VMS is exactly a system that when you have a context switch, the memory's physical memory locations belongs to the process being switched out. The whole residence set, meaning that the physical page that the process can occupy must be swapped out, be returned back to your secondary storage, and those are problematic. So that's why that's actually the why of the the Unix system design, because as we said, the original Unix is a swap-based system inherited from the VMS VEX, VEX VMS, right? So whenever you have a context switch, you have to swap the whole process out from the memory. And it's really efficient if you have frequent context switches. Remember what we just said, right? In past about the situation called saturation, right? And it also implies that, but another thing, right? Because this paper already fixed that problem, it implies that in modern Unix or Linux, we don't do the swap-based thing, right? So, well, in the past, the context switch overhead is really high. Part of the reason is because you have to swap out those pages. But right now, this paper is telling you that you don't have to do this, right? And that's the what this paper is going to do, right? And that's part of the reason. So first of all, you don't have to swap out everything when you are context switching out. And the second contribution of this paper is that we are telling you it's possible to implement an efficient page replacement policy without hardware support. So that's the why of this paper. Two contributions: a page replacement policy doesn't need hardware support, and then a virtual memory management system doesn't require you to swap out the whole application when you are performing a context switch. So let's see how it does that, right? So the first thing we talk about, and actually it's a very important contribution, is the page replacement policy. So after reading this paper, show me by how much you'll understand the page replacement policy of this paper. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's go ahead and start the group discussion. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so, it's kind of interesting, huh? So, which team want to share your thoughts? Okay, so I have Rogelio, I have Emmanuel. So, what does your team think? Rogelio.
Our team thinks that two of these are correct.
Two of these are correct. So, what are the two?
4 and 5.
4 and 5 allocated to a fixed set of pages, and the page replacement policy guarantee the response time of short programs. So how about blue team? What do you guys think?
We thought number 5 is incorrect because it was mentioned in the paper. That's how we knew about the
Okay,
5.
so how about number 4?
Then number 4, we saw there is not a fixed set. It is like dynamically it adjusted, and so it's not fixed. That's what it make it not be correct.
Okay, so actually your team saw there's nothing correct.
Yes. We at the very
so
last minute,
see.
yeah.
Okay, so let's see what's the answer, right? So first of all of you agree with that it's not using LRU, right? So Rogelio, what's the policy has been used?
FIFO. And I think you've mentioned that like 5
Is
times.
it FIFO? Is it FIFO
Well,
in the paper?
It was saying that because there's no reference
this
information.
policy is actually not FIFO. This is called clock algorithm. That's a different policy than FIFO. Right. So, okay. So let me walk through this. Okay. Thanks for your answer. So this paper, they actually propose a new algorithm for page replacement policy. And this page replacement policy is good because it claims that its performance is as good as LRU, but you don't need any hardware support. So let's see how it works. So the basic idea of clock algorithm, well, although in hardware implementation, it doesn't look like this, but let's consider but I just want to let you feel like why it's called clock, right? So you can consider all the physical locations you have, and you can make them a circular queue. So it's actually a circle like this, and then you have a needle, and for each circle, each page you have a reference bit attached to each page table entry. So in your page table entry, you set if the page have been referenced before. And what you will have to do is that every time when you are trying to replace a page, there's always a clock needle pointing to the page that you are going to replace. However, if the page that you are pointing to have a reference bit that has been set, you are not going to replace this page. Instead, the only thing you did is that I clear the reference bit. And then I will migrate my needle to the next page without a reference bit set. So in this case, we will clear the reference bit for A and B, and then we will move our needle to C. So C will be the page that has been selected as swap out. And however, the reference bit for A and B, they are all closed. And the next time when you have a page, you will start with D. However, the D here is also referenced. So you will clear the reference bit and then select E. So that's how the clock algorithm working. So the basic idea is very simple, right? And there's no hardware like timestamp required to support this policy. Instead, for LRU, you either have to use a very complex like linked list, or you require a timestamp and sort all of them. right? But this policy is very simple. All you need to do is to attach a bit to your page table entry, which you already did every time when you allocate a page, like the valid bit, like the permission. So it's not too big an overhead. So, and that's something you will definitely have to do every time when you read a page table entry. So no hardware support is necessary. The overhead is really low. So that's a basic idea of clock algorithm. So right now, I want you to recap on this, right? So LRU, we have 7 references. But if you have clock algorithm, how good is that? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I believe this one should be a relatively shorter discussion. So go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it seems like the answer is somewhat diverse. So, which team would like to share? Okay, Andrew, what does your team think?
Our team think the answer is 7, but I think we can go follow your instruction or like do it one more time to see what's the exact answer.
Sure.
I think it's also
Okay,
between 6 or
so
7.
okay, so we believe the first 3 is about the same, right? But
Yeah.
what's different is that right now for when we in the second cycle, right? The page 2, because we reference it again, right? So the reference bit has to be set, right? And then now for the fourth cycle, well, the third cycle, because we still have space. So although 1 is a page fault, but we don't replace anyone, right? So now what's interesting is happening in when we try to access the fourth cycle, right? So who are we going to replace at this moment?
Since the pointer now point to 2, but the reference bit for 2 is a set, then we go to next point, next location,
Right. So
next
we are
page,
going
which
to
is
replace
3. Yeah.
3. Okay, so there is a page fault and 3 is kicked out. Now we are at next cycle. What are we going to do?
I think for next cycle, since 2 still in the physical page, we just set the reference bit of 2 to set.
Are we going to kick out anyone?
No.
Are we going to change the needle position?
No.
Okay, so now in the next cycle, when we have 4 incoming, who are we going to kick out?
Since the needle is now pointing to 1 and the 1 doesn't have a set bit, so we kick out 1.
Okay, so page fault, right? So now we are having 7. We are having 5, right? So anything happen?
5 will be set because it's a reference.
And
And
where's the current needle?
Stay at 4.
Not pointing to 2.
Mm,
Should be pointing to 2, right?
Oh yeah. Because last time we inserted 4 into the thing.
Right. So that's what happened in the next cycle, right? So how about when we have 3? Page fault or
Since
not?
3 is not in there, so we encounter a page fault. So we're trying to kick something out, and I believe it's gonna be 4.
Okay, so we kick 4 out.
Yeah.
Now we have 2. Is 2 still there?
Yeah, 2 still there.
Is 5 still there?
Yes. And
is 2 still there?
Right. Yeah.
So how many do we have in total?
We have 6 actually.
It's actually 6, right? So your walkthrough is correct, but your answer is not correct, right? So be careful about that. So clock is pretty, yeah. So as you can see, right, the clock is pretty high performance, even though it doesn't require very exhaustive sorting like LRU, but it works as well as LRU, and in this little case, it even outperforms, right? So so that's why clock is used in this paper, because first of all, the most important thing is that it's as high performance as LRU, and the second thing is that it doesn't require the hardware support. Another thing that this paper is trying to use to improve the performance is again, the page caching, or say the free list in general. So so if you remember the idea of free list from the last paper, right? The basic idea of free list is that in a memory space, in addition to the memory locations that a process can use, we maintain 2 lists. One is the free list, meaning that the list of the page that's currently in the free list is free for any process to use if necessary. However, it can also contain pages that are just retired from, or say replaced from a process. And a modified list is another kind of a list saying that this set of pages, they need to copy when you want to kick them out. You have to put them, their data, you have to write back their change in a disk. So that's a separate list, right? However, with this kind of page caching idea, what's really good is that right now saying that in process A, I have a page fault, meaning that I need another page. Instead of immediately kick out a page from my working set, I can just use one page from the free list and then contribute a page that was originally belongs to my working set to either modify list if it's modified or free list if it's a clean page, right? And if I have another page fault, for example, for process B, again, I can just contribute, I can just grab a page from the free list to serve my request. However, when I have another page, I need to contribute another page to the free list in this sense. But if the page that I contribute to free list is later used, then I don't need to go to the disk again. Or if there's another process need that page, it just overwrites the page since the page is not belonging to the process B anymore. So that's the idea of free list. So thinking about this idea, right? Thinking about this idea, the Unix paper actually integrate this idea pretty well, and use them more broadly in their policies. So right now, why don't you spend a few minutes to look over this sentence and see how this paper is trying to even further use the free list for. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like we need a short discussion for this question. So now go ahead. Maybe let's try to limit the discussion in 2 minutes. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so which team would like to contribute your thoughts? Raise your hand. Okay, I have a Rogelio. You're always fast. What do you think?
Well, we think the answer is 2. So C.
Okay, so what are the two?
Actually, I'm sorry. I incorrectly read number 4. I think it might just be B. 1, 2, and 4 are all incorrect.
Okay, so others, do you have other thoughts?
Our team thought number 2 is also incorrect.
Okay, so can you explain more?
We thought because swapping it just if we need to swap, it means we need to reach out to disk. So and if we need to do swap, so it doesn't matter. It doesn't help anyway.
Okay, so how about the other three? Do you think all the rest three are correct, or do you think there are still some of them not correct?
The fourth one, we also agree that is not correct.
Okay, so is there any evidence why this is not correct?
Because you just explained that in the list from they can other processes pages can go to the list as well. That's why we thought then we can use it.
But it's other purpose, right? Not other processes.
Okay. Then I that was my I wasn't paying attention.
So what do you think now? Do you still agree that this one is correct?
I need someone from our team to help me out.
So
okay.
Wait.
Okay, Rogelio, you have some thoughts.
For number 4 is not. I think it's incorrect because we mentioned that free list can be used as a disk cache.
Okay, it can be used as disk cache. So 2 and 4 now you all agree it's not correct. And Rogelio, you said that you don't agree with the first one as well?
That's correct. That's what I said, at least.
What's the purpose of free list?
If I actually give it some thought, it's so that you can basically.
So with free list, what happens when you have a page fault?
It's an available page to be used, meaning you can. Right. Yeah. So maybe 1 is actually correct.
Right, so 1 is actually correct, right? So if you look at this one, right, it's actually, the first is actually the main reason why we want free list. And the second one is what Blue Team just said, right? That's completely depending on how fast your disk, right? And 3, I'm glad that at least you agree this is correct because it means that you guys did read the paper, right? Because for the page replacement policy, that's actually triggered in Unix is actually triggered by another thing which we will later talk about. And you can use the pages as disk cache, right? So thanks for both teams, and I think you guys have a good discussion on this. So the free list here is that the trick. So the whole picture of Unix policy here is that they use the clock policy to decide what page to swap in and swap out. However, when are we going to swap in and swap out? So the thing is that the Unix system, they also have a free list, which always provide you a set of free pages. So it only triggers the clock policy whenever the number of free list is too small. So when your number of free pages, or say the number of pages in your free list is lower than a threshold, then we trigger the clock algorithm. So it's not the page fault trigger the clock policy, but the number of the pages in free list would trigger the clock policy. And whenever your daemon running in the background feeling like the number of free pages in free list is too low, you just trigger the clock policy in the background whenever your disk is under a low overhead, and then you try to replace those pages. And as they mentioned, the free list can be used as a disk cache. And because we are running out of time, but you can use free-m instruction under your Linux, you will see how aggressive your Linux is trying to use free list as a disk cache right now. And so we haven't talked about this and the answer of this question. But after you look at the whole idea of the clock policy and the free list, you will soon figure out that first of all, it used clock policy, not LRU, and it triggered the page replacement policy are triggered when your free list the number of pages in free list is low, right? And it doesn't require anything like a timestamp in your page table entry. That's too much of an overhead. You only need a reference bit, right? And then you can adjust. You can just get the page from the free list whenever it needs, right? So there's not really a distinction of a fixed set of pages belongs to each process. Whenever you want a page, just grab it from the free list, right? And the page replacement policy doesn't guarantee the response time for short programs and as the paper said, right? So had no requirement for guaranteed response time as in real-time applications, right? So that's what the paper said. So actually, for the answer of this question, 0 of them are correct. Although they all sound like, well, they all sound like a correct statement in some system, but it's not a case for the Unix system, right? So so that's the whole picture of the Unix virtual memory system. So right now, but even though this system this idea sounds great, but it still has its drawback, right? So that's why later on there's another paper by John Hennessy. If you don't know who is John Hennessy, shame on you, right? He's talking about a WS clock policy, and a clock policy. You probably already know, right? But before we start talking about the WS clock policy, let's still have a brief recap. So far we have learned a few policies like, and those policies that we can aggregate them into 2 sets. So first of all, there are local policies, meaning that whenever you want to replace a page, you just select a page from your working set. That's a local policy. So that's used by VEX and the original Unix. However, there are also global policy, meaning that whenever you want to swap out, right? Because we trigger the swap in, swap out whenever the free list, the threshold in the free list is low, instead of the number of pages in your working set require to fit in a new page. So in this way, right, you are selecting a free page in a free list, which can be coming from any of the process that has been using before. So it's global policy because you select pages that could belong to anyone, right? But local policy means that you are selecting pages belongs to the process that requires the page, right? So for Mach and Unix, they belong to the global policy, right? So, however, this kind of these 2 policies has its own drawback and advantage when we are dealing with systems. So right now, I want you to spend some time looking over this issue, and maybe you will figure out that in the local there is an advantage of local policies. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so looks like we do need discussion on this question, but we don't have a sufficient amount of time. So why don't we invite some of you to just share your thoughts with us? Okay, so I have Rogelio. Can I invite some others to discuss as well? Okay, so I have Sadaf. I have Xingyun. All right. So why don't you just have a discussion in front of the whole class?
Okay. To start, I think 2, 3, and 4 are probably correct. I'm not so sure about. I'm not so sure about the first one.
So Xingyun, what do you think?
I agree that 2, 3, 4 is correct.
Okay. So how about Sadaf?
I thought all of them.
All of them. So you think the first one is correct as well. So why don't Rogelio and Xingyun, you don't agree with the first one?
Yeah, if the workload of switching and swap is too high, the CPU cannot utilize efficiently.
Right. So here's the answer, right? So if you remember what you have read in the textbook, right? So when your system is overcommitted to memory, right? Well, in the very beginning, your CPU utilization will keep climbing, but at some point, your CPU utilization will drop like this, right? And this is because the phenomenon called saturation. So what does that mean by saturation? Is because when your system overcommitted your memory to task, then you have to spend a lot of time paging in, page out, right? Instead of making meaningful progress. So turns out that your running process is waiting for the data to come in and come out, and then after your data coming in, okay, your slot arrives, right? So you have to switch out. So turns out that everyone is not making meaningful progress, right? So that's called thrashing. And another term that another term that has been frequently get confused with thrashing is saturation, which you learned before. So by saturation, it means that when we are using switching policy like round robin or whatever, right? You do have the context switch overhead, as we just mentioned, that you have to reset your page table. You have to bring in those page tables, the page table nodes, and you have to restore those register values, and those are overhead. So it turns out that you spend a lot of time in dealing with those overhead. So, but no matter it's because of a context switch overhead or because the paging overhead, if you have a lot of processes, that's what end up with, right? So not only your paging making your operating system not making progress for your program, but also the context switch overhead will kill you, right? So both phenomena will make your process utilization very low, and both phenomena will make your process not making progress. However, they come from different backgrounds. So thrashing is because you are overcommitted to your memory to too many processes. And for saturation, it's because you overcommitted your processor resource to too many processes. So in fact, you are spending more time in context switch. Right, so that's the whole difference. That's the main difference between these two ideas, but they lead to a very similar phenomenon that your processor is busy working on something, or your processor is idle waiting but not contribute to the running program. Right. So what will happen is that, as what we just discussed, 3 of them are correct. The first one is not correct. So the WS clock policy is actually talking about how can we remedy this, right? Because if you have global policy, right, processes with huge demand, they can grab more pages. However, if you have local policy, every page would at least be guaranteed that when I schedule you for running, because you are going to be given a set of memory pages for you to work, right? So it will better prevent thrashing phenomenon. So the basic idea of a working set algorithm is that, well, first of all, we try to adjust the demand of your applications by initially when we schedule this process to run, we give you a basic set of pages, and whenever whenever we found that there are always some pages that in your working set has not been referenced for a long period of time. So for example, we give you we give you a few sits, right, for your startup company, in saying that in some places, right? But whenever we found that you are not able to fill your seats with employees, we take those seats back. So that's the idea of a working set policy, right? And but how we adjust this is by when we see, well, you have a page that has not been referenced for a certain period of time, we just return it to the free list. And as we just mentioned, right, if somebody wants a page, they can grab it from the free list. So that's the whole idea how WS clock policy would work, in a way that we use the working set policy to decide how many pages can a process use, and return a page to the free list if in your process there has someone hasn't been accessed for a certain period of time. And if the free list that we have is lower than a threshold, we still trigger the clock policy. So the whole idea is very similar to the clock policy that we just mentioned. The only difference is that in the very beginning, we still assign a set of pages to each process and gradually adjust the process's working set according to if there are pages that hasn't been used for a certain period of time. And if a process want to grow its working set, is by when you have a page fault, you can take a page from the free list. So in this way, you have the feeling that I steal a free list from steal a page from the free list from another process that hasn't been using a page for a long time. So that's the whole idea of WS clock. There's nothing too different. The basic part is just like the clock policy, right? So, and this is actually the most frequently implemented policy in a modern operating system. So the modern operating system, they are not using LRU, they are using clock policy. They are not using pure local or global policy. They are using a working set clock policy to get benefit from both sides and avoid a drawback from each side. Okay, so if you don't mind, to let me spend a few more minutes, I'm going to walk through a sample midterm with you. So this is just a sample midterm, and I do recommend you to practice it before you take the real midterm. And regarding the real midterm, as we said, cheating is definitely not allowed, and it's so easy to tell who is cheating, who is not. Believe it or not, last time during CS203's final, I caught 2 cases of cheating, and definitely there are some consequences of that. For example, so don't that happen. I don't like that situation. And we will release the true midterm tonight, and it will do February the 15th, end of the day, minus 1 minute. And you will have to find a consecutive non-stopping 80-minute slot in this period of time. And we don't accept any late submission. And the format is that you will have 15 multiple choice questions, 4 short answer questions, and 3 free answer questions. So and for those short answer questions, I know a lot of you always ignore the word short. So I want to make sure that you know what does that mean by short. So by short, it means that you have to explain everything within 30 words. And actually 30 words is already a pretty tolerant policy, because when I took a class in the operating system class in UC San Diego, the professor actually wanted us to minimize our answer in 10 words. So 30 is already very tolerant to you, right? So so first of all, you will have 15 multiple choice questions like this. So make sure that you go through all of them before you take the midterm, right? And I have this set of 30 words questions that you have to practice and let me know and let me know in the midterm, right? So like and those are very easy to answer. So I believe you can walk through them later through the slide. The slide will be published on the webpage. So don't worry about that. I always publish that within an hour after the lecture. So don't worry about it. And also there are some questions that we would like to invite you to think more deeply, like what is the real meaning of multi-variable scheduling policy trying to do, right? And what happened during a context switch and how expensive is the context switch, right? And page replacement policy, you have practiced it, so it shouldn't be too much of an issue for you. And as I said, right, there is a homework for you to do. If you have multiple producers and consumers, what are you going to feel, right? And like this kind of question, I think is probably not too difficult for you. And how to implement a simple shell, which already demonstrated in the class, and how can we redirect the program output to a file? So those are possible questions that we could potentially test you in the midterm. So announcement. So no lecture this Thursday because you are going to spend 80 minutes to any time you like before the end of the day on February the 15th. And reading quiz is due next Thursday because you will drain out your energy for the midterm. And our office hour is on Monday 3 p.m. And Thursday 9 a.m. And project, again, make sure that you install the virtual machine and you got the x86 64 version. That's about it. Otherwise, enjoy the rest of your week. Enjoy your Chinese New Year. Enjoy your Valentine's.
祝福大家 Happy New Year！我是一只鸟。